is Keith Benedict, and this is my lesson on achieving linearity. Before we get started, we have to understand what linear regression is. Linear regression is the process of finding a straight line, as by least squares, that best approximates a set of points on a graph. For example, in a perfect world, which we don't live in, the value of home increases linearly. So if you buy a home in 1990 and it's now 2005, the growth over the years would have been linear. Predicting the price of a home given X years is the idea. Now here's our problem. We don't live in a perfect world. Not all data trends linearly. Data can be expressed graphically in many different ways, like exponentially, quadratically, logarithmically. However, data can be manipulated to linear models through transformations. Now, what are transformations? Transformations of explanatory x and response y variables make data more fit to a straight line. This can be proven with the r and r squared values. The correlation coefficient, which is r, tells you the strength and direction of data, and the correlation coefficient of determination, which is your r squared, which tells you how much variation y can be accounted for by x, or in simpler terms, how good a predictor x is of y. Now here's how we transform. To transform, there's two methods concerning us right now, and that is the exponential model and the power model. For the exponential model, only the response variable, the y, is transformed, and for the power model, both x and y, your explanatory and response variables, are transformed to achieve linearity. Now, for a tutorial, you're going to want to grab your TI-84 calculator. Alright, you're going to want to turn it on. Alright, and refer to the slides, PowerPoints, for the examples and a better visual. Alright, so our example. A home in Madison, Georgia was built in year 2000. Transform the data using the exponential model. Now, for the exponential model, just as a refresher, it can commonly get confused with the power model, with the exponential model only transforming y. Now, with that being said, our given equation, y hat is equal to a times b to the x. Now, to transform the equation, we're going to want to take the natural log of both sides. Alright, then once we take the natural log of both sides, only x will be transformed and y will be multiplied times the ln of b, which is our slope. Alright, with our data, what you're going to do is you're going to want to plug in your data to your calculator. So you're going to hit stat, edit, and then the first two lists, for the first list, you're going to want to put in the years, and for the second list, you're going to put in the home prices. So if there's year 1 through year 7, and it goes from $16,000 all the way to $1,024,000. All right, now we're going to open up our third list. Now this is very important. This is crucial. For our third list, we're going to hit the LN button on the top of it. We're going to take the natural log of the second list. The reason why we're taking the natural log of the second list is because the second list is our response variable, which is what we're trying to transform when we're using the exponential model, excuse me. So you're going to hit LN, you can hit second, L2. Now that gives you the transformed numbers for the y values. Now we can view our previous equation, y is equal to 2 to the x, by just simply graphing it. To the x, like so. You're going to hit y equals, you're going to plug in your equation, then you're going to hit graph. Now that's the graphical display of the line, and that's the scatter plot display of the line. You can't really see it, but it's like increasing. It's not a straight line, just like this one is increasing and it's not a straight line. Now that's the problem. We're going to fix that problem. Now, you're going to go to the stat function again and go all the way to test, scroll down to linear regression t-test. It's the F. You're going to plug in your first two lists. You're going to put in L1 for X list and L2, list 2 for the Y list. It calculates. Then when we look at our summary statistics, the R and R squared, R is equal, which is the strength and direction is about 0.88-ish. Then for R squared, it's 77%, which means that X is not the best predictor of the Y values. Now we want to change that. So with our transformed Y values, we're going to go back to linear regression t-test. And this time we're going to put in the first list, but we're going to put in the third list instead of the second one. All right, you're going to hit calculate, then you're going to scroll down to your R and R squared summary statistics. And as you can see, they're both 1, which means that strength and direction is perfect. Correlation is awesome. And that means for the R squared, that means X was a perfect predictor of predicting the prices of the home values, which is Y. Now that's for your explanatory model. Now once we graph that, as you can see, it's a little hard to see. Now it's a straight line instead of a curve like it was last time. This is achieving linearity with the exponential model. Now for our power model, you're also going to refer to the slides for that example. It's more or less the same thing, but this time we're just transforming the X and the Y, and we're going to be using the same example. We're going to be using the same house in Madison, same data we're plugging in. All right. So you're going to want to go to click stat, go to edit. We have our first two lists. We have our third list, which is our transformed Y. Now for our fourth list, this is important. We're going to click LN of list 1, which is going to give you the transformed data of your explanatory variables. Hit enter, and boom, that is your transformed X values. Now, more or less the same thing as last time. We're going to hit graph, and we're going to hit Y equals. You're going to plug in the same equation you did last time. Now we see that's our graph, still curve. All right, and we want to fix that. So what we're going to do is we're going to go to linear regression t-test. We're going to see how well X and R and R squared are of predicting the Y values. So we're going to plug in our first and second list. As you can see, again, it's the same numbers, the 0.88 approximately, then we have the 77%. Now we want to improve this, so we're going to hit stat. We're going to plug in the data for our fourth and third list. Stat, down to linear regression t-test. The faster way to do this is click alpha, then F. Linear regression t-test, we're going to plug in our fourth list into this one, and our third list right here where the Y list is. Go click calculate, we're going to scroll down, and as you can see, your R and R squared values are better. The strength and direction of the line, of the data, is 0.96, which is almost perfect. Then our R squared percentage is about 92-93%, which means that X is almost a perfect predictor of Y. Now when we look at our graph, it's gonna plug in the line for you. And we're gonna look at the graph, and it's also a linear line. See that? Yes. It's a linear line with the fourth and third list. Now, why do we want to achieve linearity? We do it for the sole purpose of just trying to express different graphical displays as linear models. All right, so what story did the results convey? So between the power model and the exponential model, the exponential model yielded better results because it actually made a perfectly linear line compared to the power model. So for this specific data set, the exponential model was a better fit than the power model.